Welcome back to this almost last part of the series on the thermodynamics of the biosphere. In this series, we want to look on this video, we want to look at the role of humans in the Earth system. Humans in the end are also part of the biosphere. And so, we can now apply this thermodynamic view of things to what humans actually do. And we'll see humans, of course, and human societies consume energy, and this energy comes somehow out of the Earth system, and we can understand a lot about what the impacts are of our species on the planet. And we can also see what the solution should be for the future, for a sustainable future. Okay, I want to start again coming back to Schrödinger and his view of what is life. And we have seen that already in an earlier video that life is basically chemical disequilibrium. And so we can also think of us humans as being chemical disequilibrium. I mean, this is what we do. And to maintain this chemical disequilibrium, to maintain our individuums, what we need is to eat, we need to eat food. And food is energy with low entropy. And the human metabolism converts this on one hand side to waste. I mean, mass with high entropy. After all, mass is not lost, but only converted. And we produce actually heat. I mean, this is sort of metabolic heat release, actually quite substantial for a human being. It's about 80 to 100 watts, just sort of the basal metabolic rate. So clearly thermodynamic, clearly to do with energy conversions. So when we now think about what we do, and want to bring it into sort of a planetary context, we've already seen sort of also in the context of the Earth's history that basically what life did over the millions and millions of years of the Earth's past is basically take CO2, use photosynthesis, perform work, create disequilibrium in form of reduced carbon compounds like carbohydrates, hydrocarbons, and releasing oxygen. And so that disequilibrium, that's chemical energy that in the end we consume. So human societies here shown in the yellow box, I mean, we consume this disequilibrium in the form of food to maintain our metabolisms. And by that we produce CO2, so we do the reverse. And we, since industrialization, we have, let's call it externalized activities. So, we don't use the biosphere as modes of transportation, but we consume energy to make our life easier. We heat rooms or cool rooms. We use energy to move around for mobility. And for that, nowadays, that's dominated by using hydrocarbons, that is fossil fuels. And these release CO2. So let's call that externalized activities. And when we take that together, then, what humans do is they basically deplete the disequilibrium that the biosphere has developed over the millions of years. Now we want to go a bit more into detail and look at, for instance, at the first part here, the food production, and we can sort of follow the energy from the solar energy input to photosynthesis, to food production, and put this in proportion to human metabolic energy needs. So we've seen that photosynthesis has a very low efficiency, not directly a thermodynamic limitation, but an indirect one, because thermodynamics limits transport, and that's limiting photosynthetic activity on land. So we can go from the solar energy input here, put it in units of terawatts, so that's integrated over the whole planet. Then some of it is being absorbed, is about absorbed at the surface. Then you can say, okay, about a quarter is land, but then only a third of the land is productive. And then we have an efficiency of perhaps 2% or so, and then we get sort of an estimate for how much geochemical energy in form of carbohydrates photosynthesis produces on land. Substantially less, because of little area and little efficiency. And then we have also seen that half of that actually is used by the plants themselves. So the biomass production is about half. Then when you add to this sort of the area over which actually humans use land for agriculture, that's shown here in this map on the right, that's about a third of the area. and then we get to 25 terawatts. About a third is typically converted into actually crop yield, and that brings us down to 8 terawatts. And if we use that yield to feed livestock, a typical rule of thumb is that to maintain the metabolisms of the livestock, you lose about a factor of 10. So from the 8 terawatts, we get down to 0.8 terawatts. And to just give you proportions here, when we, on the other hand, use the human metabolism, we have about 8 billion people on the planet times 100 watt. We also get about the 0.8 terawatt. So that's the metabolic need. On the left-hand side is the food production. And you can already see that, metabolic needs of human beings is significant at the planetary scale. Maybe a quick note here. So one implication one can see here from directly is that if you don't, or if you eat less meat, then actually we would need less land to feed humans, because there is another energy loss by using or feeding livestock and maintaining livestock. And if we now take that sort of to a bigger picture, it actually shows a dilemma or a real problem. And that is, so solar radiation produces this useful energy by photosynthesis, and that feeds the biosphere, or humans appropriate it and humans consume it. And that means that, the more humans consume the energy that photosynthesis generates, the less there is left for the natural biosphere to feed food chains and maintain biodiversity. So in other words, our living comes at the expense of a reduced, shrunken biosphere, if you want. In the end, it's of course all dissipated into heat. And so in the end, it's all, coming back to thermodynamics. Okay, and potentially, human activity could have a feedback on photosynthesis in terms of, for instance, improving conditions to enhance photosynthesis. That would be good, because then there is more for all. Or we can also have detrimental effects, for example, climatic changes in terms of, for example, impacts on the water cycle that could actually deteriorate. This could make things worse. Okay, so that's the human energy needs for the metabolism. The other part, and that's actually the bigger part, is our externalized activities. So we use fossil fuels, and we use it to for the industry, we use it to heat and cool our rooms, we use it for mobility, and we use it in power plants, thermal power plants, to convert it into electricity, and then use the electricity for various things like computers, light, cooking, and so on. Now, with the power plant, we have already seen that there are limits. This is where thermodynamics comes into play, and that out of heat, you can only convert a certain fraction into useful energy. Now, because we burn fossil fuels, that means that those that carbon that the biosphere has sort of deposited in, co-work with the geology, buried it. Well, we take it out, we burn it, we deplete that disequilibrium, we release CO2, and that causes the global warming. And that, of course, has some impacts in the end on the biosphere, because the warmer temperatures also come with changes in the hydrological cycle and probably conditions that are not so well suited for the biosphere, as we have seen at the end of the last video on Earth's history in the context of the Gaia hypothesis. So humans deplete that planetary disequilibrium. But the other thing, and I think that's again coming back to the thermodynamics, is that actually this combustion technology is actually quite inefficient. You can see this on the one hand side. We already looked at power plants and the efficiency that limits the power plants, thermal energy conversions. You have a lot of waste heat, and in the end, our mobility with combustion engines also, actually, it's even worse. Usually only less than 20% is used in the car to move it, and 80% is waste heat. And when you then also consider that photosynthesis creates biomass with an efficiency of 1%, you can actually already see how inefficient that is. Now, for both, I want to sort of give a little bit of a bit more depth. So in terms of global warming, since I gave this course in Italy, I picked a weather station some time ago from Perugia. This is in the capital of Umbria, which is in central Italy, and looked at summer temperatures in the afternoon, so maximum temperatures in summer months, using a weather station that has been operating in Perugia already for some time. And so I looked at 2 time slots, from 1961 to 1990, that's 30 years, that's what's called the climatological reference period, and from 1991 to 2020. And what you see here are sort of the blue is the distribution of minimum temperatures, in red the maximum temperatures, and you can really see the effect of global warming at this weather station. You see the shift of the darker blue and the darker red distributions. Especially the maximum temperatures have increased quite substantially by about 3 degrees, almost 3 degrees over 30 years. That's really, really strong. And that is not just the increase in the greenhouse effect, but also amplified by a reduction of cloud cover. And to just give you an sort of a simple manifestation of what that actually means, I also showed here on the top sort of the cumulative distribution function. So that is basically averaging or integrating these frequency distributions, and with this one can infer extreme temperatures. And so what in the 1960s and 70s was extreme, let's call that the upper 5%. Well, what was extreme in the 1970s, let's say, were maximum temperatures above 33 degrees centigrade. And these days have increased in the 2000s to actually be more than 20%. Yeah? So more than 20% of the days were actually really extremely hot. And so nowadays, when you have temperatures of 36, 37, or even 40 in the summer in central Italy, it's absolutely not normal. It's a manifestation of this severe global warming. Okay, now the other aspect that I'm going to talk about is why thermodynamics, or why combustion technology is actually really inefficient. And I think this is a really nice application of entropy. So I want to sort of take a moment to explain that a bit in detail. So we've seen, way in the beginning that the expression of Clausius, basically, that entropy is the energy released divided by a certain temperature, divided by the temperature, and that's then it's actually being used to derive the Carnot limit of a power plant. And basically, the idea is that you get lower entropy and more use out of that heat, the hotter the temperature is, because then, when you divide that released energy divided by a hot temperature, then your entropy is lower and you can make more use out of it. And so the question is, what's actually the maximum temperature at which you can combust? It's not a new question. It's actually a well-known concept. It's called the adiabatic flame temperature, or you can also call it maximum combustion temperature. And it's being set by, basically, you want to have the least mass involved in the combustion process to maintain the combustion process. And that gives you a temperature. That temperature is typically really high. I mean, it gets a few thousand degrees centigrade, but quite often that temperature is not used because metal would melt, for instance. So in other words, in principle, during combustion, you can release heat at quite a low entropy, but we don't use it. And so when we don't use it, well, we are basically wasting it. And thermodynamically speaking, we basically produce entropy, making the energy less usable. And especially when we use combustion to heat rooms, and when we talk about room heating, like in Germany, In winter, you talk about 20 degrees, not 2000 degrees. And so in other words, you waste that whole temperature difference, you waste the low entropy in maintaining a slightly warmer room compared to the outside. Now, inefficient use is usually avoided. Natural evolution throws these things out, and we can actually already see this in certain technology. For instance, in the way we generate light. Because, back in the old times, we used candles. So we used also combustion to produce light in a very inefficient way, because actually what happens is, you have the flame, and the light is actually produced by the rising soot particles that are so hot that part of the emission is in the visible spectrum. But in the end, what lights do is they produce a lot of heat and very little light. Then came the light bulb. Well, the light bulb uses electricity. The filament in the light bulb actually was quite a bit hotter, and so it released more light, but still a lot of heat. And nowadays, we actually use a technology from quantum physics, which we call LEDs, light-emitting diodes. It's a semiconductor thingy where we use electricity to generate mostly light and a little bit of heat sort of in the electronics and so on, but it gets a little warm, but by far not as warm as a light bulb. And so, when we think back at the definition of efficiency, so we put the use in proportion to how much energy actually went in, then, we evolved to a lot more efficient technology by switching to electricity and by using some technology that is rooted in quantum physics. When we now take this to our energy system, our primary energy system, well, we also have photovoltaics. And photovoltaics is another manifestation of quantum physics. We've seen it in the very beginning. That's also semiconductor technology where light is being used directly to raise electrons, and so you can basically then suck away the electrons, put them in the grid, and create electricity, so useful energy without creating heat. And that's a much more efficient way when you think about that photovoltaics can already achieve more than 20%, theoretically more than 70%. When we compare that to photosynthesis, then this is a much more efficient use. When we then use electricity for mobility, we can achieve efficiencies of about 90%, and then you also have regenerative braking. So in other words, when you brake, you can basically generate electricity again, or we can use heat pumps to generate room heating. That is also way more efficient, because out of, say, 100 units of energy, you can get 400 to 500 units of heat, because they are heat, that's heat at high entropy, because we only want to maintain a relatively little temperature difference between the outside and the inside. So overall, drastically enhanced efficiency when we go from combustion to electricity, and we can understand that directly from thermodynamics. And now, when we think back sort of at the grander scale, we've seen in last video on the biosphere that basically we can think of that the biosphere, is a thermodynamic process that enhances the conditions to enhance its activity. Well, so we can also postulate or formulate here that, from a perspective of thermodynamics and the whole planet, advanced civilization, they should figure out how they can utilize and enhance the environment to sustain themselves and to sustain more activity. So in other words, to also generate a positive feedback. So we use some forms of the environment, we use energy and resources from the environment, but our feedback should be such that it actually enhances the environment to allow the Earth system to perform more work. And I think this is sort of quite a basic insight for how we can steer into a more sustainable future. And actually, at the end, I want to sort of well, I mean, when you see these news about global warming and, that the water cycle gets out of band with, torrential rainfalls and greater droughts and this strongly enhanced extreme temperatures in Perugia that we have just seen about a moment ago, that sort of seems all a little depressing. I leave politics out for the time being. And so I want to end this with a little bit of let's say, a sign of hope that it actually, some things may actually already act actually more than we notice. And that brings me to to another concept that actually is in population dynamics very well known, and that is that things usually don't grow linearly, but they quite often grow what's called logistically. So what I show here on the left is an example of such a logistic growth. That's again, very well known in population dynamics, where initially something grows exponentially and then eventually it reaches a carrying capacity. So here I put, the K is the carrying capacity, N is whatever grows. And this is something that people who study technology also use. They call it the diffusion of innovation, and they describe it as an S-curve. And when you look at data or observations, and you know that things will grow logistically, or basically, initially you have an innovation, and then, it seems like it doesn't really pick up. But the exponential growth is something that we always underestimate. So initially, we don't actually notice as much because it's so small, and then eventually it really rapidly rises, and eventually saturates before it when it actually dominates the market. And well, why am I talking about this? Well, the reason why I'm talking about this is because you can see this breakthrough currently happening with renewable energy. So photovoltaics and wind are at the moment exponentially, or more precisely, logistically growing in generating electricity. So what I show here is there's a certain kind of transformation. So one doesn't look at the fraction by which photovoltaics and wind generates electricity, but rather the fraction generated by photovoltaics and wind divided by the remaining technologies. And then one can show that this is an exponential function. So I plot a logarithmic axis here, and one can look at the electricity generation of different countries or different regions. So what I show here is red in Germany, and orange the EU, green is Italy. Then I also have India, US, China, and global. And what we see is that they all follow this logistic growth, and approximately at similar rates. And I find that really quite stunning. I mean, there's a certain time offset. So, for example, in Germany, where I come from, we are almost approaching 50%. So that's almost the turning point of the logistic growth. And, because of that, we also have problems with the grid and so on. I mean, there are some new problems coming up. And we are sort of a little bit ahead of the curve. Other countries are a little bit behind the curve. But overall, the slope of this increase is actually quite similar across countries. And I find that quite reasserting. And in the end, I mean, this, one can also understand it because especially photovoltaics is a really cheap technology to create electricity. And so it will dominate in the future. There's no question. And when you start generating the electricity, when you start generating useful energy in form of electricity, and we've just seen that there are good motivations thermodynamically to go to electricity and avoid combustion. Well, then we avoid combustion and we avoid emitting CO2. Then global warming sort of more or less is going to stop if we make this advance. And so we can actually also put this again sort of in a broader perspective of planetary evolution, and we can sort of this is sort of coming to work done with a dear colleague, Adam Frank from the US, and Marina Alberti, where, some years ago, we, in part of a paper, we actually classified different planetary objects by how they actually generate work out of sunlight. And so you can think about planetary bodies like the Moon or Mercury that are just flying pieces of rock. They perform no work. They just absorb radiation, emit radiation, that's end of story. Then you can think about planets that may have an atmosphere and may have motion, like Venus and Mars. So there are power plants working there, generating useful energy, but otherwise nothing much happens. Then you can think about the Earth, where you have useful energy being generated by power plants, but also by photosynthesis. And then when you look into the future, you can think of another form of useful energy being generated by photovoltaics, like an advanced civilization. And so that would also then follow the sequence thermodynamically to increasing power of a planet. So, but let's get to the end here. So when we want to summarize this effect of humans on the Earth system, then we can really use this picture of the thermodynamics of the biosphere, because what humans do is they just dissipate useful energy. We don't generate it. So this comes at the expense of the biosphere, and it comes at the expense of this planetary disequilibrium in form of hydrocarbons and oxygen. By consuming food and fossil fuels, we deplete this planetary disequilibrium, and the answer to this is, well, stop combustion, go to electricity, use photovoltaics, and make the Earth more powerful. So this is more or less the end, but I have a short summary video to complete this short series